fairly empty region of space-time.
Yeah, we believe we could have passed through one during this conversation.
Yeah, we could have passed
A big
one
enough black
through.
hole wouldn't have known it.
And yeah, and in fact, cosmologically, we probably did pass through someone else's horizon while we were having this
Right,
conversation.
right. Sure.
So the problem which I and several colleagues set out to solve a few years ago was, can you have one of these maps that goes from more to fewer degrees of freedom and still in some sense preserve the information that you really care about?
Yeah.
And now I want to explain why this going from more to fewer is radical. I think it's probably good if I say a little bit more about how error correction works in general, if you don't mind.
Please.
Yeah. So let's first think about classical error correction. So say that I'm NASA. Well, I don't know. I don't know if NASA still exists. What is it? Yeah, we have to
Well,
check
what time
the
is
news.
it?
Yeah, I don't know. Yeah. But okay, assuming that NASA still exists, and that they haven't fired the people who want to communicate with Voyager 2, then there's some people who want to communicate with Voyager 2, who was launched
The
in, back in
fuck
the
is this
70s and
saying?
is now very far away and has a very small satellite dish, and we want to talk to it. And of course, if you just send a message once, like, it's probably not going to get through. That dish is very weak, and it's so what do you do? How do you communicate? Well, there's a very simple answer, which is you just send the message 100 times.
Yeah.
And each bit you send it 100 times. Maybe half the time nothing gets through. Of the times that it does get through, you look at it, and some of the bits are 0, and some of them are 1 because it got flipped along the way or something. But then you just do majority vote. All the bits I got, if I got more 1s than 0s, I assume the message was 1, and if I got more 0s than 1s, I assume the message was 0. So that's called the repetition code. That's the simplest error correcting code. You just send the message a bunch of times, and clearly the more times you send it, the better the code. And so that's the fundamental point, is that usually error correcting codes are about redundancy. Okay.
Sure.
And when you have a quantum computer, now it's interesting. So in fact, people thought you couldn't do error correcting codes with quantum computers because in quantum mechanics, there's a no cloning theorem, that you can't make copies of an arbitrary quantum state. And so you can't do a quantum repetition code. And so people thought, well, maybe that means that there's nothing that you can do. But here is where entanglement really saves you. So that entanglement, as we discussed before, is this kind of super strong form of correlation in quantum mechanics. And being correlated is not quite the same thing as being copied, but it turns out that it's good enough. Okay, and so that